So guys, this is gonna be a quick video, I guess, where I wanna share with you something I've just found in Java. Like I didn't know it existed. Something that solves locking. I just came across it. I don't use Java that much, and it honestly blew my mind. So I'm learning about Java more, and I'm taking a different approach to learning about this. I'm taking low-level concepts and trying to learn about them in Java, of course. And I found this thing. Okay, let me destroy this. I found this thing that's called atomic variables or atomic integers. In this case, you can do atomic doubles and so on. And which basically does, when I learn, I just take small things and try to, throw them into haiku and Claude haiku and get a quick explanation. So what are they designed for? Of course, there's thread safe. The problem with multi-threading is race conditions, as we talked about in the previous video. I found this thing, as I said, which is called atomic variables, which allows multiple threads to safely read and write to the same variable without race conditions. How? You can say, okay, we use locking. This is the thing that's universally used, but I don't know much about this, but if it's what's in my mind, it's absolutely insane. Instead of using synchronized keywords or locks, which is what I just said, can be slow because they force threads to wait for each other. That's the polling mechanism. And that's a big, a big, uh, yeah, a big con when it comes to the locking thing. Atomic variables like atomic integers and so on use low-level CPU instructions called compare and swap, the CAS, to ensure thread-safe updates. That's amazing to use something uh, on the CPU that's that low. When threads want to update an atomic variable, it doesn't lock asynchronous. It doesn't lock anything. Instead, it attempts to swap the old value with the new value. And if another thread changes the value in between, the operation fails and the thread retries automatically. That's absolutely amazing. Like I never heard of this and it's honestly blow my mind. It's motivating me more to learn more about Java. This happens at the hardware level and pretty much faster than traditional locking because threads don't have to wait around. They just keep trying until they succeed. Um, I don't know if you gain much performance from this comparing to traditional locks because uh, with locking you're basically updating, but with this thing you will update, but if it was changed in between you will roll back, so your update is no longer valid. But I don't think it's much of a performance jump here. I don't know. Okay, just some technical stuff. Let me explain. Let me prompt the model. Do we get much performance jump when we use atomic integers versus traditional locking? I'm using haiku in this to get fast responses. Of course, the accuracy is gonna be lower. Yes, you do get a performance jump with atomic integers over traditional locking, but the size of the jump depends heavily on how much contention you have, meaning how many threads are fighting to access the same variable at the same time. Alright, so with low contention, where only few threads are occasionally accessing the variable, the performance difference is minimal because neither approach is really being stressed. Yeah, that's the thing. If you're locking your value or your variable, uh, like basically the fighting doesn't happen as much. But with moderate to high contention, where many threads are constantly trying to update the same variable, atomic integers can be significantly faster, sometimes 2 to 5 or more, because lock serialize access only. One thread can execute a critical section at a time. Okay, there is the concept of ownership that we talked about in the previous race conditions video. So the others have to wait and get blocked, which involves an expensive context switching. Okay, okay, now I see. With atomic integers, using compare and swap, threads don't block. They just keep retrying the operations optimistically, which is much faster, even though it sounds like it would be slower. Downside is extremely high. Okay, so now that's the beauty of the OS. If you know this stuff on the low level, like you know what context switching is. We explained this in a previous video. Sorry, I'm a little bit sick. Um, so now you understand when you see, you appreciate this atomic integers thing, and it's my first time learning about this. Like I said, I'm I decided to go heavy in Java this year. Uh, I just want to learn a new language, and I didn't feel I was ready to learn Java, like to get deep into Java before, because I didn't understand much about the OS. Like I don't want to just memorize things, I want to understand things. Okay, if compare and swap operations can become a bottleneck because of cache coherency issues and excessive retries, but this is rare in practice. So the practical answer is use atomic integers when you have a lot of threads competing to update the same variable frequently. And traditional locking when you have complex critical sections with multiple operations that need da da da. Okay, I think this one can cause a problem. This atomic integers can cause a problem on the cache of the CPU because you have multiple cache layers and they communicate via a bus. Uh, yeah, it's just a layer, when a variable in a layer or a value in the cache of a layer gets updated by something, it basically sends a notification through the bus of the CPU to notify the other cache layers and say, okay, invalidate this thing, and yeah, basically that's the next time they will try to access it, they will see it as invalidated and refetch it again. That's if I have a good memory. That's what happens. I didn't touch on this stuff for a while now. Okay, let's see. Does this cause an issue on the CPU cache layers if multiple threads are fighting over it? Yes, absolutely. That's what I said. This is a real problem called false sharing and cache coherency overhead. That's the thing it was mentioned before. When multiple threads on different CPU cores are constantly fighting over the same atomic integer, the CPU cache coherency protocol has to continuously synchronize that memory location across all the L1, L2, and L3 caches of each core. So, yeah, that's what I said. If I'm updating here again and again and again, I'm rolling back. That's critical because I have to notify the other ones to change the cache or invalidates the cache each and every time, and that's very expensive, which creates a lot of overhead and can actually tank performance. Every time a thread updates a variable, it invalidates the cached copy of all the other cores. Yeah, that's exactly it. Forcing them to fetch the updated value, blah blah blah. So that's basically it. And I will try to look more into this stuff, and I will update you whenever I find something very interesting. So that's it, and See you again.